I'm sorry, dear participant, we have start in 1:10 p.m. Sorry, because we have technical problems here. We do apologize. Thank you. Okay, the time shows 1:10 p.m. So we can start immediately. Okay. Assalamualaikum warahmatullahi wabarakatuh. Good
Waalaikumsalam
afternoon,
warahmatullahi wabarakatuh.
the Honorable Head of the Chemical Engineering Department of Universitas Diponegoro, Professor Dr. Insinyur Aprina Purbasari, the Honorable Head of the Doctoral Programs in Chemical Engineering, Prof. Dr. T. Aji Pastianingrum, the Honorable Professor Dr. Muhammad Zaini, who has graciously facilitated the invitation to our esteemed speakers today, and our distinguished guest speaker today, Professor Insinyur Dr. Lau Chung Lim from Tyler's University, Malaysia, who is joining us virtually. And to all the chemical engineering students, Himpastegma committee members, and all the guest lecture participants attending both in person at the third floor meeting rooms and virtually via MS Teams this afternoon. First and foremost, let us praise and thank God Almighty for His grace has allowed us to gather today with His name, May 6, 2026, for the guest lecture on advanced drawing technology. My name is Tubagus Ryan Fitra Sinuhaji, and I will be your moderator guiding this hybrid guest lecture session until 3 p.m. So before we proceed to our main agenda, we will having a welcoming speech. I would like to respectfully invite the head of the doctoral program in chemical engineering, Prof. Dr. T. Aji Presenting Room, or maybe Prof. Jenny to deliver the opening remarks. Prof. Aji or Prof. Jenny, the floor is yours.
Sebentar ya, nanti ditambah Prof. J. Oke, terima kasih. Thank you very much for Professor Chung Lim for your time to give a guest lecture for our student at Chemical Engineering Department, Diponegoro University. I am a head of doctoral study program in Chemical Engineering Diponegoro University. And this lecture was attended undergraduate, master, and doctoral student, and vocational student. We hope that this lecture about advanced drying process will provide additional knowledge for our students. Thank you very much for Prof. Chung Lim for attention in this lecture. Thank you. Monggo, Prof. J, silakan.
Yeah, thank you so much, our honorable lecturer today, Professor Insinyur Dr. Lo Chung Lim from Tyler's University, and all of the students. I appreciate for your attention today. This session, Professor Lo Chung Lim will deliver the speech and lecturing. It's about advanced drying technology. Perhaps the session will be held in one half until 2 hours maximally. I expect all the audience can get the points from the Professor Lo Chung Lim, having experience in the drying technology and application. I thank you for Lo Chung Lim for the availability to deliver the lecture today for us. I think your lecturing today can give us the high contribution, especially to enrich our students in terms of drying technology and development. Thank you so much, and the time we will send back to Master Ceremony. Thank you.
Okay, thank you very much, Prof. Aji and Prof. Jenny, for the warm and inspiring opening remarks. So moving on, before we begin the presentations, I would like to share the few housekeeping rules for today's event. For offline participations in the room, please switch your mobile phone to silent mode. For online participations, please keep your microphones mute during the presentations. You are encouraged to turn on your cameras if your connection allows. And the Q&A sessions will be held right after the presentation is completed. Ladies and gentlemen, drying technology is a crucial process in the chemical engineering industry, essential for both energy efficiency and maintaining product quality. Today, we are very fortunate to be joined by a leading expert in this field. He is Professor Dr. Lo Chung Lim, PhD. Currently, Prof. Lo serves as the Executive Dean of the Faculty of Innovations and Technology at Tyler University, Malaysia. He is a chartered engineer and chartered scientist registered in the UK, as well as a professional engineer in Malaysia. He is highly active in professional bodies, currently serving as in the chairman of the ICME Malaysia Board. Since 1998, Prof. Lo has led numerous applied research projects focused on solving industrial problems, particularly utilizing fluidized bed technology and advanced drying technology. His research spans the preservation of local fruits, enhancing cocoa bean quality, and optimizing edible birdnest processing without the use of hazardous chemical. His immense dedication has resulted in dozens of international scientific publications and various patents. Without further ado, let us proceed the main event to our honorable speaker, Professor Lo Chung Lim. Welcome virtually to Universitas Diponegoro. We are very honored to have you online with us today to learn from your extensive expertise in advanced drying technology. Prof. Law, the screen is yours, Prof.
Yeah, thank you, Saudara Tubagus. First of all, I would like to take this opportunity to thank University Diponegoro and also Professor Aji, Professor Jani for inviting me to share my experience in this session. First of all, let me share my screen so that you can see my PowerPoint presentation. Tubagus, can I check with you whether you can see my screen?
Yeah, Prof. The screen is can be seen.
Okay, thank you.
You're welcome, Prof.
Ladies and gentlemen, salam sejahtera. Tubagus has already introduced me, so I'll quickly go through my self-introduction slides. But first of all, I would like to briefly introduce to you Taylor's University and the Taylor's Education Group structure. So here, the university is owned by Taylor's Education Group, and within the group, we have Taylor's University, Taylor's College, British University, Vietnam. This is a campus in Vietnam, and it is owned by Taylor's Education Group. On top of that, the education group has another division, which is the school division, where we operate the international school, the secondary school. And so these are the schools that are operated under the school division of the educational group. And the university has the mission and vision statement. And for us, we aim to be a leading international university. So everything that we do, we look at how we can compete with other university at the international level. And one keyword in our vision statement is purpose-driven. So we mentioned to our students that, when they learn something, they need to understand the purpose. We also coin this as a purpose-led learning. And within the university, it is very important that we also practice the values. So I just want to share with you one of the values that we practice within Taylor's University, that is always putting students first. So that is the philosophy of Taylor's University, where we implement student-centered learning. And within the Taylor's University, we have 4 faculties, and I'm serving Faculty of Innovation and Technology. So we have 4 faculties and plus a Taylor College. So Taylor College offer diploma and also pre-U studies. So within the Faculty of Innovation and Technology, we have 4 schools: Computer Science, Engineering, Architecture, Building and Design, and the Design School. So the Design School offers very creative programs such as fashion design, creative media. So these are the programs offered by our Design School. Taylor's University is ranked 27 in Asia in the QS World University Ranking. And just now, Tubagus already introduced me. I just want to share with you that we have 4 schools, which I mentioned to you just now. And within the faculty, we have more than 270 staff, academic and support staff. And within the faculty, we have approximately 4,500 undergraduate and postgraduate taught course students. Externally, I serve in a number of roles. For instance, I serve as the Senior Associate Editor for Drying Technology. I serve as the head for Sydney Accord, Dublin Accord Review Panel. And this panel has been tasked to evaluate engineering New Zealand. This is a society or professional body in New Zealand. And on top of that, I also serve as the leader for chemical engineering team for the professional competency examination under Board of Engineers Malaysia, as well as associate director for the engineering accreditation department. And about my research, I focus on two main areas. Number one is on technology development. So over the past many years, I look at how to design, fabricate, invent machine, mainly for the drying of biomaterial, and then use the machine, use the technology to process various types of food. Here you can see I classify the research material that we have investigated over the past many years into different categories. They are, and you can see from here, herbal products, fruits, agricultural products, animal products, and noodles. And in recent years, I focus a lot on heat pump assisted drying. And later, I'm going to share with you some of the research findings that we obtained pertaining to applying heat pump assisted drying to various types of bio-origin products. But first of all, I would like to share with you a bit on supply chain management. And this is to allow us to look at the big picture of how we manage the supply chain and where we need dehydration, where we need drying, so that you are able to picture the overall picture of the food supply chain. So if you look at the whole supply chain, it starts from harvesting. Yeah. So it means that when the product is ready for harvesting, we harvest the product at farm, and then we may need to do a bit of pre-processing. For instance, we do a bit of handling, storage, and transport of the product where we harvested from the farm. And then the material is subjected to primary and secondary processing. And after that, distribution to the market. Okay. And after that, the material may be used for cooking, for preparation of food. And at the end, deliver to the customer or the consumer. So during this process, this is the big picture. And now we would like to go into this particular section, primary and secondary processing. So in the primary, we have processes such as cleaning, pounding, drying, sieving, and grinding. Okay, and in the primary processing, there is a need to look at drying of the material. If we want to sell the product in fresh form, of course, there is no need to remove water from the material. Yeah. Now, if we look at secondary processing, these can include mixing, cooking, molding, cutting. And next, I would like to talk about causes of post-harvest loss. So after we harvest the product from the farm, due to various reasons, the product may be damaged, may be denatured. So therefore, we have post-harvest loss. And these are the causes, for instance, high temperature after harvest. It can be due to sun exposure. It may be due to lack of cooling during the cold transport or cold storage. So because of that, the material can spoil or damage or denature. Another reason is because of loss of water. And the loss of water can be due to high temperature that evaporate water from the product. It can also due to low RH or poor packaging that results in loss of water. The third reason for post-harvest loss is physical damage. For instance, it might be due to poor packaging, right, which then damage the product physically, or due to inadequate transportation that results in the physical damage of the product. Reason number 4, decay. Decay can be due to high temperature. So this is linked to the first cause, right? So high temperature result in the removal of water, which then result in the decay in the product. And this can also due to poor sanitization, or due to physical damage. And again, you see that this is linked to the third cause. And finally, it can be due to inadequate drying and also inadequate dry storage. And inadequate drying, it means that the product may not be dried properly, and the product may have a high moisture content. And because of high moisture content, water is available, for microorganisms to multiply and multiply during the storage or during transportation, that can result in the decay or damage of the product. And because of moisture is available, and because it is due to the inadequate drying, so it then encourages microbial activity. And when there is microbial activity, then it results in the damage or decay of the product. So since we understand the causes of the post-harvest loss, then we can look at techniques how we can reduce the losses. Okay, for instance, just now I mentioned improper packaging, it can result in physical damage, it can result in decay. So what we can do to mitigate this is to improve the packaging. By improve the packaging, we can reduce water loss, we can reduce physical damage, and therefore we are able to reduce the deterioration, especially to the food product quality. Technique number 2 is to look at cold storage. Just now, because of high temperature, so product can damage or decay or denature. So if we are able to make sure that the cold storage is operating well, then we are able to reduce the losses. And of course, when we look at the cold storage, we want to look at the low cost option. Some of the cold storage can be high cost. So in this case, we need to look at the optimum solution for the problem. Okay, and number 3 is to improve drying technology. And therefore, this is linked to the topic that I want to deliver today, that I want to share with you today. So if you look at drying technology, and if we are able to improve the drying process of the biomaterial or the products, then we are able to minimize the impact to the product quality. So here, when we mention product quality, it can be related to color, texture, the shape, and also the amount of active ingredients in the products that we process. And finally, there are also other processing techniques which allow us to reduce the losses in order to prolong the product shelf life and in order to improve the product quality further. And next, I would like to share with you how we manage this supply chain. So when we want to manage supply chains, there are 2 directions. Number 1 is the dry management. The other one is the wet management. So if we look at food, after we harvest the food from farm, the food begins from here with warm and wet. Warm, this refers to the surrounding temperature, the ambient temperature. Wet, it means that the food contains a lot of water. That is the initial water content. So if we have no intention to remove water from the food product, then what we can do is we go for cold chain management. Cold chain management. We store the product in cold storage, keep the temperature low, try to minimize the microbial activity, right? So that's why when we go to supermarket to purchase fresh food, you see that those foods, they are kept in cold storage. So the low temperature will minimize the microbial activity. Of course, eventually, after a very long period of storage, although under low temperature or cold storage, the product may subject to the degradation in quality. So that is cold chain management. Now, if again we start from here, the food with high moisture content at ambient temperature, one way is to apply dry chain management, where we remove water from the product. So when we remove water from the product, water is not available in the product, and therefore when microorganism wants to multiply, they want to grow, they multiply, they need water for the metabolism. So when there is no water available for this microbial activity, then microorganism will not be able to grow, to multiply. Okay, so therefore, the moment we apply drying or we apply dehydration, we remove water from the product becomes a dry product. Okay, so when the product becomes dry, of course, we need to look at the moisture content. And when we look at the moisture content, we also want to know the corresponding water activity. So later, I'm going to share with you how we look at the water activity at the same time, the moisture content. So that is the dry product where we can store the material in dry form for an extended period of time. But of course, for long-term storage, what we can do is we can produce dry product, remove water from the product, then keep at the low temperature. By doing that, the product is dry, stored at low temperature. We are able to prolong the shelf life of the product, for a very long time. So basically, that is the supply chain management. This is the slide that I mentioned to you that when we want to look at the product shelf life, we want to look at water activity. So water activity is normally used by food scientists. Yeah. So for chemical engineer, for food engineer, normally we look at moisture content because we need moisture content to allow us to design dryer, to design unit operation to process food material. Yeah. But for the food scientists, they prefer to look at water activity. So for me, because I work on the design of dryer, I also work on the food quality. So therefore, I take into account these two aspects, moisture content and water activity. Now, this diagram is to show you the water activity, and let me explain further. So if you look at this water activity and the microorganism listed here, here this means that if the water activity of a particular material is 0.95 and above, this means that Pseudomonas, E. coli, and etc., they can survive. They can survive, they can multiply. The moment we reduce the water activity to below 0.95, then this group of microorganisms, they cannot multiply. Yeah. But of course, if I keep my food product below 0.95, it is safe from Pseudomonas, E. coli, and etc. Yeah, but it is not safe from other group of microorganisms. It is susceptible to Salmonella, botulinum, lactobacillus, and etc. Okay, so therefore, if I look at the bottom line here, 0.6, if I'm able to keep my food product at water activity that is below 0.6, then my product can be kept for a very long time. Yeah, because none of the microorganisms listed here will survive, will multiply. They won't. Right. So one key message to bring home today for this session is that water activity shall be 0.6 if you want to keep the product for a very long time. Now let us look at some of the samples, and the corresponding water activity. If you look at this, canned pet food, 0.85 or higher. So this means that the canned food, if they are exposed to, say, environment, say, surrounding, exposed to microorganism, then they can easily decay because 0.85 is somewhere here. So this canned pet food is susceptible to this group of microorganism, right? This microorganism can survive, can multiply, and therefore damage or denature the food. So where do we draw the line? We look at 0.6. So 0.6, this is where we draw the line. This is where we draw the line. And here you can see dry pet food, right? And here you see canned pet food. Because canned pet food is still very wet, contains of water. So if we can it, right? So we are able to protect it, but the pet food is still very wet. So the moment we open the can, it is exposed to microorganism from the surrounding, then microorganism can multiply and grow and grow. And because of microbial activity, so the pet food can decay. Right? So that's why any question? So one way is to dry the material so that the moisture content is low enough. Therefore it drives the water activity to a lower level. Next, I would like to draw your attention to this diagram. This diagram is very useful, especially to food scientists. So for us who wants to process food, we also want to look at this to understand the undesirable process or reaction that can occur to various types of food. Okay, so how do we read this diagram? Yes, we start from water activity. So water activity 1.0, it means that this material is saturated with water. It contains a lot of water. right? So when the material has a lot of water, yeah, when the water activity is in this region, this is a high water activity region, yeah, maybe from 0.8 to 1.0. And you can always cross-check with this 0.8 to 1.0, right? This. So it means that these materials is susceptible to at least this group of, or these categories of microorganisms. And in this region where the food material has very high water content, where the water activity is high, they are susceptible to enzymatic reaction. They are susceptible to this reaction, yeah, which is the non-enzymatic browning, right? So it is the non-enzymatic reaction that can cause browning to the product. And as also at this region, it is also susceptible to lipid oxidation. This means that if the product contains high content of lipid at high moisture content, yeah, lipid can easily oxidize and and decay or result in the decay, yeah, or denature the products. When the moisture content is reduced further, yeah, and therefore it drives the water activity to this region, you can see that the degree of enzymatic reaction, the degree of hydrolytic reaction, yeah, they decreases. Okay, they decreases to a low level, right? So you can see that for these three types of reaction, non-enzymatic browning, hydrolytic reaction, enzymatic reaction, they reduce when we reduce the moisture content of the material. Okay, then in this region for lipid oxidation, it's very interesting that the lipid oxidation decrease, but at a very relatively low moisture content, yeah, and the further reducing the moisture content, you see that the lipid oxidation, yeah, it increased, right? So this means that we need to look at the content of the material. For instance, if our material, it contains oil, it contains lipid, even though we are able to keep the moisture content of the product at a very low level, we still need to pay attention to lipid oxidation. Just like, for instance, if you have something like, in Malaysia, we have muluku. Of course, this is the Indian product, the fried product. Just imagine you have something that you fry, you fry something with oil. So after frying, we have the fried product, but it contains oil. And imagine if you keep the fried material in a storage for an extended period of time, yeah, slowly it will develop the rancidity flavor as well as odor. This is because of lipid oxidation. Okay, so I think many of you might have experienced, some of the fried material that you purchase, you bought from market, and you keep it too long, right? The product develops some undesirable flavor, undesirable odor that is due to lipid oxidation. So the keyword is the oxidation. Therefore, if you want to avoid lipid oxidation, we just try to keep the material, the product, in an environment that doesn't have oxygen, so that lipid oxidation doesn't occur. So therefore, to conclude on dry chain management, we need to thoroughly dry our product after harvesting. We want to reduce the moisture content so that the water activity is below 0.6, so that we can store the material for a longer period of time. And of course, after drying, we also need to look at how we keep the product, how we store the product. We have to store the product in a dry condition so that the product doesn't absorb moisture from the surrounding. We want to avoid re-wetting of the material, because when the material is re-wetted, the moisture content increases. When the moisture content increases, the water activity increases, right? When the water activity increases, then it is susceptible to microbial activity again, right? So we always go back to the diagram that shows where is the safe level, right? So by doing that, we want to make sure that after drying, we want to keep the product properly in order to prevent growth of mold or the generation of mycotoxins or aflatoxin due to microbial activity. Next, I would like to quickly go through drying principles so that you have a better idea about drying. Now, drying, of course, we know drying pengeringan is something that we do every day. Yeah? For instance, we wash our clothes, then we hang our clothes under the sun. So to ordinary people, to laymen, they probably understand drying as, you just put something under the sun, or you subject something under very high temperature, then that is drying, right? So some people may say to you, drying is so simple, just high temperature. This may not be the case. Yeah, in fact, today I'm going to share with you low temperature drying. That is my research work, and I have a lot of research finding that I want to share with you, in the later slides. Now, let us look at the drying mechanism and principle. Just take a look at this diagram. Say we have a material, and it contains moisture, right? So when we look at drying, we know that we are dealing with heat transfer, especially when we subject the food material or the drying material under high temperature. When the material is under high temperature, there's temperature difference. The temperature difference drives the heat transfer from high temperature to low temperature. So this heat transfer can be done either through convection or through conduction. When the material touch hot surface, that is conduction, or through radiation. When the temperature is very high, right, for instance, more than 100 degrees C, then the radiation contribution is higher. Then at the same time, during drying process, moisture is removed from the material, and then carried away by air. So in this case, we are also dealing with mass transfer, and mainly evaporation on the surface. But also at the same time, if the material is thick, for instance, apple, right? So there is also moisture movement within the material, and most of the time it is by diffusion, right? So here we are dealing with diffusion. On the surface, we're dealing with evaporation. Okay, and some of the material, if they're porous, there may be capillary flow of liquid slowly from the internal to the surface, and then evaporation of moisture. So if you look at this is already very complex. Heat transfer, mass transfer, different type of heat transfer, different type of mass transfer. Yeah. So if you look at the matrix of the drying material, on the right hand side here, so there might be different type of moisture movement, from the internal to the surface. Just now I mentioned to you capillary flow, right? So again, if we want to look at this angle, there are a lot of study that we can do. And again, it is not a very simple process, not a very simple unit operation in chemical engineering. In fact, it is a complex unit operation. Next, we want to look at the drying rate. So here, when we look at this graph, it is drying rate versus moisture content, right? So how do we read this graph? We start from the high moisture content. So when the material has the initial moisture content, and the initial moisture content is high, say this is the initial moisture content. So just imagine when we dry the product, the drying rate is very high, right? So when the drying rate is high, here is higher drying rate. So, and if there is a short period of time where evaporation occur, then we have constant rate, because the constant rate, it depends on the evaporation, right? Then after that, the surface is dry. Here you see no more surface water. When we have surface water, then you see evaporation, right? Then it also means that when you plot drying rate versus moisture content, and you see constant rate period, then you know that the material is covered by a layer of water, and the mass transfer at that period of time is evaporation. But the moment that you see that the drying rate is reducing, when the moisture content is reduced, then you know that the surface is dry already, and the reduction in the drying rate indicates that it is actually the diffusion that drives the internal water to the surface. And then because of that, we have falling rate, okay? And this period is called falling rate period. Next, I would like to share with you some key aspects related to drying. Number one, when we look at drying, number one is to look at whether the material has toxic or flammable solvent. But for food product, most of the time, this would not be the case, right? So therefore, when we evaluate the product and immediately when we establish the fact that the product doesn't contain any solvent or any solvent within the product that is toxic or flammable, then we don't have to look at this. But if we dry something, say for instance, we dry chemical, or we dry some material which is not food product material, but it contains liquid, and the liquid is either toxic or flammable, then we have to be careful. We cannot just dry the material, because the moment we dry the material and the solvent evaporated, right? So the solvent is toxic. When it is evaporated, it becomes vapor, and the vapor is toxic. If the solvent is flammable, then the vapor is flammable. Yeah. So in chemical engineering, when we need to deal with toxic vapor or toxic material or flammable material or flammable vapor, the key is to contain it. Yeah? So we have to apply containment. Okay. So in drying, then we will look for vacuum dryer or freeze dryer, because vacuum dryer and freeze dryer comes with a condenser. So what we can do is we can condense the toxic vapor after we evaporate the toxic substance. It becomes vapor. So we use condenser to condense it, so it becomes liquid. So liquid that is toxic, so we need to contain it. We cannot discharge it to the environment. We cannot discharge it to the surrounding because they are toxic or flammable. Yeah, so therefore, most of the time, if we are dealing with toxic or flammable material, we will opt for vacuum dryer, freeze dryer. Yeah, because they have the condenser unit. So condenser unit, we then can contain the material easily. Now, second aspect to look at is whether the materials contains variable solvent. Yeah. So